You've been listening to the future for a while, so now we're going to go full steam into the past. A couple of words to get into the change of direction. My undergraduate class had its 50th reunion last summer, because back in the days of the early web, I was probably the only one in the class who knew HTML. I got volunteered to be the webmaster. So I spent actually 3 or 4 years digging up history, running up to 1964, which was my class. And so when Kelly invited me to give a research and career overview, that sounded kind of interesting, because I could start where the other interests had ended. Get my watch on California time. And review 50 years of history in about 50 minutes. So there's a certain amount of compression that's involved. And whenever you have these old guy talks looking back on the past, there's the problem that things are not now what they were then. And so I've tried to collect anecdotes and other bits of wisdom that I've tried to distill from my career and point them out, and hopefully try and hit some things that stay true even as other things change radically. So the more things change, the more they stay the same, is sort of an introductory comment. Okay, Prelude, before my career really started, and I have a tendency of pacing when I lecture, so I'll try and stay within your range, but okay. In high school in 1957, I read an ad in Scientific American for a computer that you could have at home. And so I'd argue of all my colleagues, I'm probably the one who first had a computer and met the works, at least, of Claude Shannon. This is what it looked like, and the ads that I saw, these aren't exactly the same, but they're pretty much what the thing was about. And the connection with Shannon was, this was developed by a guy named Edmund Berkeley of Berkeley Systems Incorporated, somewhere, I think in Illinois, he was centered. But I learned from Shannon's widow Betty that he bugged Shannon constantly for help in putting this thing together, putting together a booklet of 400 games and projects that you could do on that silly computer. And with the computer came a copy of Claude Shannon's master thesis in the form that it got published in. And I like to remind people that the first guy to actually do logic design using Boolean algebra, realizing that a binary number system was the right thing to use to design digital circuits. So this, of course, as a junior high student, was a little bit over my head, but it was kind of fun to read. And this is the copy that I had originally. It was just one of those things I didn't lose. And so I encountered Shannon pretty early. In high school, I started learning about computers because my brother was teaching a class at San Diego State, and that piqued my interest even more. And I also got involved in ham radio, which used to be, when I was young, probably the best entry for wannabe techies and geeks, and didn't use it a whole lot, but at least got started. As an undergraduate, I was on a co-op program, which meant every other semester I went off and worked, and that was highly valuable in balancing my theoretical tendencies when I was actually in school. And also a thing that I think had a very big impact on me was I took off a semester in my junior year and went and just traveled around in Europe. And Vendangeul, that's a fancy name for grape picker. And that taught me I really did want to go back to college, finish my degree, and not be a grape picker for the rest of my life. Busker was a street singer, and that was fun. And I also learned something about picking your job right, because that paid about 10 times what picking grapes did. And I wasn't a good enough guitar player to make a living at it, but it certainly gave me a great sanity preserver and a hobby. Graduate school, I took a whole bunch of programming and probability and random processes that also helped direct me, and I needed to find a master's thesis. And my first try was Bob Kahn, which presumably you know about. He and Vince Cerf are the generally acknowledged real fathers of the internet because they developed the TCP protocol. However, he was a brand new assistant professor and it just failed miserably. He constantly asked me to do things. I tried. He wasn't happy. I tried something else. So I needed to find an advisor. And while he didn't end up being my advisor, my path really started by taking an information theory class where I met Bob Gallagher and started taking classes that I guess one point is these were the classic books that were used back then. The date of this was September 1964. And I'd like to point out this is one of the applications that he mentioned would probably come in the future was biological systems. So he was very prescient in those days. Also economic systems. So the classic figure one from the information theory class, and just after I took that class, I went off to work at Co-op, and they gave me a project of analyzing a communication link between a sonobuoy. It had a mic under the water and then the buoy on top to transmit information. And using my newfound information theory, I pointed out that their target data rate of communication was something like 10 times the Shannon capacity as computed using reasonably good but simple models. Ergo, it wasn't possible to do what they wanted to do. But unfortunately, they'd already granted a $400,000 contract to some company to do it, and they had a quandary of how to treat this. So they solved it by moving me to a different division in countermeasures. So it was, I guess this showed me that things are practical even with very basic stuff having only had one class. But I had no thesis advisor yet, so I went back to MIT and talked to a bunch of people and finally suggested on a face that's very familiar here at UCSD, I worked on sequential decoding, channel, reliable coding, not source coding. And old computers, they were doing Project Mac at that time, Kendall Square, highly exciting. I should also mention that during that time, I encountered, when driving a date home, a drunk driver going the wrong way in a one-way underpass. Ended up by being in a hospital. He was one of the first people who visited me there, and then helped arrange for me to finish my master's thesis in the MIT infirmary. Told I was the only one who ever did that. So I've always been highly grateful to him. And then I went off for a PhD at USC, which was somewhat of a rising star at that time. They acquired a very good faculty. They recruited graduate students. I was flattered, so I went off. One of the reasons I went off was to work with a guy named Lee Davison, who was a big shot in data compression, which I thought was interesting. But by the time I had accepted and gone there, he decided not to come yet. So he didn't come until the year after I graduated. So I guess one of the morals is, stuff happens, things go wrong. I went there anyway and never regretted it. Another thing, I guess, that happens at universities, hopefully less now, I've been promised complete fellowship and admission and all of that stuff. I got there and nobody had done anything. This had all been promised by the department chair, and I went to his assistant, and it took a couple of weeks to work out all the paperwork. So that was just part of it. It all happened eventually, but I realized you can't trust promises even from powerful people. The guy who was the chair of the department ended up vice president of the university later, and I think he survived only because he had this great assistant who did all the details he promised but didn't follow up on it. I spent a couple of summers at JPL and met lots of interesting people like Andrew Viterbi. One of the regrets I have was that I read a draft of the algorithm that later became the Viterbi algorithm and didn't really get it. It was Jim Omura, who was then at UCLA, who really understood what the algorithm was doing and helped popularize it. So I'd had most of the engineering I needed. I could coast at USC after an MIT undergraduate training, so I took a whole bunch of math, including advanced probability and random processes, and that helped a whole lot. I found a PhD committee, and it included Irwin again. USC had promised before I went there that he could be a second reader. That was easy. I needed a USC person to be first reader. That was Bob Schultz. And then the third reader was Lloyd Welch, who's a Shannon Award winner, and really, as I'll mention shortly, saved me when I ran into what seemed like an insoluble problem in my thesis. And it was really Jacobs who suggested I look at Shannon rate distortion theory because, so far as he knew, nobody had really looked at it since Shannon. And it seemed to be a nifty theory that ought to have lots of applications, especially to compression, quantization, A to D conversion. And the idea of going into something that looked like it could be highly fruitful, that really the only stuff out there was the stuff by the master, including this paper. Point is, this I also kept heavily annotated, and I'll say this as a bullet later on. Go back and read the classics, because they just, and you've already heard this today, they're just amazing often in the insight and the comments, many of which don't get into the hundreds or thousands of subsequent papers on the topic. I started looking at a non-stationary process right away, the Wiener process, and was trying to extend some of Shannon's results to that. And one of the tools that I ran into that I really liked was Toeplitz forms, Toeplitz matrices. Here's an example. It's a matrix and things stay the same when you go down a diagonal. All right, that's a covariance matrix of a stationary process. And the fact that that's Toeplitz means you can pull in all of the theory of Toeplitz forms to do a whole lot of what is known about stationary processes. So most people are kind of frightened by non-stationary processes. But if you use the same class of processes that Todd already mentioned, autoregressive processes, it turns out that the covariance isn't Toeplitz, but the inverse covariance is almost Toeplitz. And so you have the power of most of the results, even when you're dealing with non-stationary processes, like the Wiener process. So that gave me a substantial portion of my thesis, extending stuff mostly to Gaussian, and some of the bounds also worked even when they weren't Gaussian. And so a comment is, when you're doing theory with random processes, don't be too unhappy if you start ending up with non-stationary ones. Because a lot of non-stationary ones can be handled with the same tools. You just need a different focus and slightly different methods. Okay, since non-stationary was so nice when I was dealing with Gaussian and similar stuff, I have to remember which button to push. I got interested in a classic, simple, discrete autoregressive process, which is the symmetric binary Markov process. And actually very little in information theory was known about this stuff. And it turned out all of the bounds that I developed worked for this. And not only did the bounds work, you could actually show that you could evaluate the rate distortion function for a non-zero range of small distortion and get it exactly equal to the bounds, and then the curve went off. And I think that was one of the first cases where anybody knew what the rate distortion function was for any discrete process that wasn't IID. This isn't IID, it's Markov. There's an IID process underlying it. It's really the transition probabilities. And that's what gives you the bound. But then showing you hit the bound turned out to be really hard. And Lloyd Welch came up with this proof, and I still don't know where it came from. It's in multi-dimensional, trying to decide when certain matrices are invertible, and then everything works. So another bit of advice, sometimes when you get absolutely stuck talking with really smart people about it, you may stumble on something that you would have never have thought of, but somebody else might. And Lloyd Welch did that. He's, as I mentioned, Shannon Award winner, so he's was a perfect guy to go to talk about this. All right, a few other things are going on in LA at that time, just to remind you it wasn't all mathematics. I lived in Venice Beach and in Manhattan Beach for a while. I won't go into detail on these, but they had an impact. I should have mentioned that that was my favorite rock and roll band at the time, because they did music that wasn't just rock and roll, but all sorts of Middle Eastern stuff. The lead guitarist is still around as a musician for professional belly dancers. But other than that, they've sort of disappeared. This was the Century Hotel. Started out as a demonstration, ended up being reported in the paper as a riot. I put this concert up there because it actually turns out I attended it, and that was where I had a blind date with Lolly, who's my wife. So I remember that concert really well. The moon landing, I was at my supervisor's house, and that was my band. That guitar, because it's now an antique, I bought it new when I retired and moved to Massachusetts. The guitar sold for over $4,500. So I guess it was nice but sad to have it go, and I was a little unhappy with it being considered an antique. Okay, I had to find a job. My advisor, Bob Schultz, through connections at Stanford, said they were looking for somebody. So that sounded good. I liked the idea of staying in California. So I went up and I gave my usual talk. And after my talk, I ended up chatting with all the faculty, one of whom was Tom Kylaf. And he's one of these sponges who absorbs everything. And so he very quietly, with a smile, pointed out that most of what I had said, he had seen in a talk given by Toby Berger at the first Information Theory Symposium, dealing with the same kind of stuff, Gaussian autoregressive and binary autoregressive. I tried to stay calm. I think I broke out in a sweat when I heard this. And then in pre-internet days, you can imagine how hard it was to get a copy of the PhD thesis that Berger had just done and the copy of the talk that he'd just given. So I pretty much dropped everything when I went back to LA and went through the paper, went through the thesis, calmed down a great deal, and found out that we did have in common Wiener processes and bounds for the binary Markov. But happily, I had extended stuff to not just Wiener processes, but all autoregressive processes, stationary or non-stationary. So I had a generalization of Berger's first result, and thanks to Lloyd Welch in that little interval of equality, I had disproved Berger's published conjecture that equality was never hit. That this was a bound and a bound alone, and even in the limit, things got close, but you never actually get equality. So, as the panic subsided, I wrote up the stuff, I sent it all to Berger, and that began an exchange, and also ended up with my having a short sabbatical at Cornell just after my first year at Stanford. I also got a job offer from Cornell thanks to that. So what had looked like a disaster turned into actually pretty good stuff, because I found it all out before I published anything. It's a worthwhile footnote that the general non-stationary Gaussian source, there was a correspondence published in the 80s, which I missed, and I certainly wasn't asked to review it, who challenged those results and provided what was alleged to be a counterexample. I didn't discover this until after 2000. But once again, I broke out in a sweat and panicked and went back to, did I really make the error? And I discovered that his counterexample actually wasn't a counterexample. And wrote a complete analysis. What do? You send it in as a correspondence? Maybe it'll go to the guy and you'll go back and forth and back and forth. And so instead, I just wrote up a paper, put his name on it with mine, and sent it to him. And so I could very diplomatically point out that what he had said in his early paper was wrong. He had derived something, but it wasn't the rate distortion function. But it was related to the rate distortion function by a specific term, which ended up having exactly what I had said it was. So with this challenge, it began a very rapid exchange to convergence. And because it involved the two co-authors, it was accepted and published rather quickly. I admit that paper was probably not read a whole lot, but it was very nice to get things right. But there is this one warning to you. There's no statute of limitations on mistakes in your PhD thesis or your first publications. Somebody may challenge you in 30 years. And so you have not only the problem of going back and remembering what it was you did, but defending against an attack from somebody. You may believe nobody's looking at some of your papers, but they probably are. I went to Stanford, and the first day I showed up, they asked me for a project number to charge half my salary to and all of my summer salary. I had no clue. This was a failure on the part of my mentor. He didn't warn me about this part of academia. And so I spent a lot of time learning how to write proposals, writing them, submitting them, even in one case taking over a large project that somebody had at Stanford and that person had left, so it wasn't really my field. And I still think that's one of the least fun parts of academia. And I found various ways to get out of it, which I'll mention to you, but it was very much part of my life for much of my career. The other thing I discovered early was the first class I taught it before, and I knew it all pretty well, so it went fine. The next class was in communications, so it was really talking about the nuts and bolts of AM, FM, PPM, and all of this stuff. And well, with a book, I had stuff close, and with a book, I think I learned it pretty well. I got many questions from smart aleck amateur radio operators saying that they had viewed FM in a certain way, and they didn't see how that was explained by the theory that I was trying to provide to them. So at least I didn't try and BS my way through it and said, I'll have to think about that and get back to you. And as I thought, obviously my best defense was to go back and learn more of the amateur radio stuff, because they have to explain all of this stuff about communications and waveforms and really doing spectral analysis when they've never had a class in Fourier transforms. And so those explanations actually are pretty good and they're pretty accurate. So I got first a general and then an advanced general license, and that made me more comfortable with that class. And the moral there is sometimes it's not so easy to stay up with students who already know the material from one point of view and you're teaching it from another. So that's part of the job that's not made clear. The other thing, and this is a regret, is I was using a small, which then meant like that, 2-meter amateur radio, calling into phone patches, which were connected with repeaters on antennas, so I could get the grocery list on my way home or chat, and it was great. We had cell phones. There weren't too many people who had cell phones, and to use a cell phone, you had to pass a Morse code test, and that sort of kept the riffraff out. I had no clue, and I hadn't acquired any clue when I was Irwin Jacobs' student of just how that field was going to explode. And I might have been influenced in my choice of redirection of research areas if I thought about that. Okay. The initial research was pursuing stuff and wrapping it up for my PhD thesis and then looking for a new area. I'm not sure exactly how I got started in it, but somehow I found out that entropy in Shannon had been taken up by a branch of probability theory called ergodic theory. So I went to one of the greats in that area, which is Don Ornstein, and chatted with him about it. And I realized that after the chat, I had almost not understood anything he had said, even though we were often using some of the same language, but there did seem to be some sort of vague connections. So instead, I found one of his disciples, Paul Shields, who had written a beautiful little book called Bernoulli shifts, and methodically learned the ergodic theory from him. And also, one of my students, Dave Newhoff, whom I saw last week, he came and visited, and I basically learned the material from scratch, and then started developing a whole bunch of interesting stuff in Shannon theory by just moving over some of the ergodic theory viewpoints. So this gives me a few things just to mention. If you don't know about, they're useful tools. The first one is the ergodic decomposition. People sometimes worry if they hit a stationary process that's not ergodic and argue about whether what they're seeing is ergodic or not. The ergodic decomposition just tells you if you have a stationary process that is not ergodic, it must be a mixture of ergodic and stationary processes. Example, flipping a coin with bias P. suppose at the beginning of time, Mother Nature chooses that bias randomly according to a uniform distribution, and then sends the result according to that bias. So what you're looking at is actually the IID process with a randomly selected bias. But your probability model says basically you're looking at a process which has a p equal a half, because you've averaged that p from 0 to 1 over a uniform distribution. But the sample average of heads won't be a half. The sample averages won't match up with your model because they're matching up with a component of that model, and you don't know what component it is, but you can learn. You can look at the train of bits you're seeing and figure out exactly what that probability is. So that led to generalizing a lot of Shannon results to stationary non-ergodic. And then we also realized that meant you could generalize them to pretty much anything which had convergent sample frequencies, and that was exactly the class of asymptotically mean stationary processes. That includes things like processes that start at time 0 and have initial conditions. It assumes things like periodic random processes. That is, the probability distributions are periodic with some period t. That got a fancy new name of cyclostationary random processes. But the periodic or block stationary processes is a very old name. You've got a chunk of stuff that's close or has similar behavior, and how do you know that if you have a source that's not exactly the one for which you designed the code, that if it's close in some sense, the code performance will also be close? And solving that came by Ornstein's d-bar distance. That distance underlies almost all of modern ergodic theory, certainly the proof of what's now called the Ornstein isomorphism theorem, which is sort of a very mathematical version of noiseless coding. Basically says if you have two processes that are in some general class called B processes, you can code a member of one into the other in an invertible way. And they use stationary codes, not block codes, which is on the next slide. It means you can go from here to there and then back again. And so if two processes in this class called B processes have the same entropy, they're isomorphic. You can code from one to the other. I guess part of my job was translating that into ordinary EE understandable Shannon coding theorems, which I'll mention on the next page. But this distance I found absolutely fascinating. Ornstein, I think, had developed it around 1973 as a tool. And as I'll mention shortly, it turns out that this is effectively a special case of optimal transport. The difference being that I don't think anybody in the optimal transport community, which was large, had ever applied it to random processes as a notion of distance. They'd all done it for vectors and for scalars. Ornstein extended it to processes, and that was kind of the magic extension that made a whole lot of things work. And I guess that I should mention, well, you've seen it. If you have a good measure on random process distance, then that gives you a geometry for writing down Shannon coding theorems in terms of this distance between processes. To say things like, if you design a code for this process, this other one is within epsilon in d-bar process and d-bar distance for it, then this code will work on this guy at least within epsilon. So it's a very useful notion of closeness. There are others that you know about, like Kolbeck-Leibler, which Todd mentioned, and I'll do a comparison shortly. Another tool was this idea of stationary codes, or sliding block codes. And in Shannon, you usually learn to map this block into this block, and then you forget everything. You go down, look at the next block, map it into that block, and you continue in that way. Sliding block codes fill a shift register and have some function, possibly in general, definitely nonlinear, which then produces maybe one bit. Then you slide everything in the shift register over by one item, and you get a new bit. So in a stationary, time-invariant, but nonlinear way, you are essentially nonlinear filtering the input to get the output. And all of the Shannon codes, channel and source, hold for this kind of coding structure, and that's the coding structure that all of the ergodic theorists use. Now, the optimal transport is really hindsight. It came decades later. I guess the first step, though, was in about 1975 when I met Roland Dobrushin at a workshop in Moscow, and we were discussing the d-bar distance, which he knew about, and he mentioned that there was something he called the Wasserstein distance that did the same thing, except d-bar was for discrete stuff and Hamming distance, and Wasserstein was for continuous stuff and a squared error. So it wasn't a metric, but it was the power of the metric, and that's good enough for most of this stuff. And so basically, I and others realized that d-bar was just a special case of that, and the common names of the distance are now the transportation distance and the Monge-Kantorovich distance. Monge's work, I think, is like 200 years old. So when this got names from the computer science department, the computer science community, like the Earth mover's distance, which they still insist on using, in spite of the fact that transportation comes from the idea of taking one pile of sand with a shape and somehow moving it in a minimum cost way into another pile of sand with a different prescribed shape. Kantorovich realized this is the same as taking two distributions and finding a joint distribution consistent with both of them that minimizes the average distortion between the two. So the idea of moving Earth is really in the idea of transportation. So I have teased many colleagues who continue to use the new name of Earth mover's distance when really this idea has been around for a long time. And as Todd said, he won the economic Nobel Prize. He shared it, and it was for the invention of linear programming, of which this distance is a key part. Okay, I think said that. You get out of all of this stuff the fact that you have a hugely general class of stuff for which Shannon theorems and Shannon practice tends to work. And it's basically mixture models where you pick a process at random. You can also get results for when you have this huge class of processes and a random switch that moves among those processes. An example is speech, because you have these little short, good autoregressive fits you use in LPC voice coding, but it changes. So you've got this window, and at short periods of time, you're looking at one process, the switch moves, and you're looking at some other. So you can do a lot with this stuff you can do with the old-fashioned stationary and ergodic. And the Kullback-Leibler distance, when I give talks about the optimal transport, people always raise that. But it has one big fault when you're trying to get a geometric measure on difference of processes. The two measures have to be absolutely continuous. That means they either have to both be probability densities or both be probability mass functions. Okay? Anybody who does source coding goes from a continuous probability measure into a discrete probability measure. And KL doesn't work. It falls apart. There is no extension that I know of that works for that. The d-bar or optimal transport distance works just fine. So you can take things that have, say, finite entropy and talk about the distance. Okay, I should add, my favorite paper of this time was I got to write a paper with Ornstein and Dobrushin. And writing with two geniuses has its problems, as you can imagine. The paper was an incredible amount of work. Had to do with synchronizing block codes on channels to produce stationary codes, and then showing you could take a limit of these stationary codes. Block codes, if you make n bigger and bigger, there's no limiting code. You can't code a whole sequence in one bang. Stationary codes you can, because you go from a block size to one thing. You can increase that block size. You're looking at more stuff for each output symbol, and then you just shift it over by one. So the key result of that was you could make the codes longer and longer, and if you were operating strictly less than capacity, you could get a 0 error code on it in the limit. So that was that's sort of like, agrees with Shannon, but there's nothing in Shannon that looks at actual infinite length codes. But one thing it taught me was it was time to change fields. Just because it was so complicated, I was getting beyond my competence, and I couldn't really keep working with these guys. And then sort of a sidelight, just to remind you, that stuff was really fun until it got too hard. But I got tripped up by something I'd written based as a generalization of my PhD thesis. And I got this letter from Kathy Martin, who before I'd never heard from, who basically pointed out that I had a mistake in an inequality. She was right, buried in this inequality or series of inequalities, which took about 10 lines. One of them was wrong, and there was no fixing it. And as she had conjectured in her letter, probably couldn't be fixed. I probably had to add a constraint to make it work. And she was exactly right. So once again, I had to drop everything because of something I'd written where I had not caught this mistake. And it was kind of sad because David Slepian invited me to have this paper in this book he was doing of classics in information theory. And I would have gotten to have a place with all of these great people, and the paper was wrong. So I declined. So it was flattering, and it was good it got caught, but you've got to check these things, and you can back up by doing what I did as I got older. Find somebody who really cares about all of those details, and is going to plow through every little step. And in my case, it was Tomasz Linder who did that. So most of my final real research papers were written with them. I had to worry about tenure, which at Stanford was then worrisome because nobody had gotten it since I got there. So I was in my 6th year, and people who had left included Vint Cerf, the other inventor of the Internet Forest Basket, who was a founder of Silicon Graphics, Ed Davidson, who went to Michigan and became the department chair. So really good people had left. I had an offer at about that time, a tenured position with a lab of my own and all sorts of wonderful things, but it was in Buffalo, and Lolly basically said if I could go if I wanted, but she wasn't. So I stuck it out, and things worked out. I got the tenure, and then I was joking with Terry Fine at Cornell that now I've got tenure, no worries. I've got a position, they can't do anything about it, I can really relax. And his true statement as a response was, no, there's always another carrot. There are other things that are going to keep you going. Very few people really retire once they become a tenured associate professor. About that time, I got interested in actual quantization in speech coding and voice coding because of my brother, who happened to be a ham. And so we were doing a lot of this conversation on amateur radio between Stanford and Santa Barbara, where he was on the faculty. And we'd often have these other amateurs interrupt, which they can, and say, I haven't a clue what you're talking about, but it really sounds cool. And so we would start this conversation with other people joining in about speech coding and low-rate speech coding and analog to digital conversion. And it was great fun. But the technical thing that had interested him was in speech coding in those early days. This is early 70s, so it's early days of really low-rate speech coding, doing something better than PCM or 80 BCM. There were many papers being published saying they were the optimal quantization of something like the key parameter vectors of, say, reflection coefficients or autoregressive coefficients. And John Markle, my brother's constant co-author, had made the cynical comment that anything is optimal according to some criterion. And so they were concerned about how do you decide what really makes sense as a criteria for optimality, and then what does information theory have to say about it. So that made me switch gears, moving entirely into speech and voice coding, taking my students with me. So let's see. Oh, I should put in a plug here. I got very much into the technical part of quantization, which I kept until the point I retired. but I also got very interested in its history. So in the 50th anniversary memorial issue of the Information Theory Transactions, I had a...
You're fine with talking, Bob. You're fine.
Okay, that's just to remind me where I am. I had a tutorial co-written with David Newhoff, which was fun to write, but I just got an invitation to do a survey in the afternoon talk at the next data compression conference. If you're interested in compression, that is just a wonderful place. It's like the information theory conferences were 50 years ago. They get a small number of people. There are not parallel sessions. There's one at a time. There are hours of breaks at the lunchtime, so the program chairs and the conference chairs can go summer skiing. For non-skiers like me, they're wonderful walks. So anyway, I immediately accepted it. I like dealing with technical history, and it's just a great place. It's always been my favorite conference. So I have to take a technical detour for a moment into quantization. I won't go very deep, but quantization is basically mapping something discrete into something continuous, as is shown here. And the implication here is that's a memoryless device, or a scalar quantizer, looks at one sample and produces a reproduction. In general, quantization, though, can look at vectors and produce vectors, or that's block code, or it can look at vectors and produce scalars, that's a sliding block code. So quantization can be quite general. I have a comment about the fact that scalar quantization seems to dominate practice, but there's a big exception. Here's an example of a scalar quantizer. Any x that falls in this interval gets mapped into that point, which is delta over 2. That's a uniform quantizer, the oldest kind, the most common kind, and I think there are references back into the 19th century of people who are doing this kind of stuff. So it's a very simple device, but because it's nonlinear, like FM modulation, it's not easy to analyze in general. And what tends to happen when you have something like that is that exact analysis ends up being very difficult, except in very special cases. And in general, you have to come up with some kinds of approximations, hand waving, maybe mathematical. There are books about how you handle memoryless nonlinearities. But what actually happened before I get into this, what actually happened, is mention the key ideas here are you have some distortion measure like squared error between the input and the reproduction, and you want to have it small, but it comes at some cost. And that cost is basically how many bits do you have to send about the continuous thing in order to reproduce it, approximately. And so you want to learn about trade-offs between rate and distortion. You want them both small. So what you're after is something that shows you how one depends on the other, or how you choose the pair. Because the smaller the rate, the bigger distortion, and vice versa. So this is really the fundamentals of both the Shannon theory and the practice. Okay, so I'm still stalling before I get into these approximations and models. This is an artifact of a bad memory. Scalar quantization has by far dominated the literature, and actually my career. And many of my students never got out of these specific forms of transform coding, which is everywhere in JPEG, both old JPEG and new JPEG. In old JPEG, it was a cosine transform, and new JPEG is a wavelet. Various forms of feedback quantization, probably the biggest one in practice currently is sigma delta modulation. Subband coding, also used a lot in audio, and various forms of adaptive and universal coding. Now, in spite of the importance in practice of that, I spent most of my career looking at vector quantizers, which are really just Shannon source codes. And I always warn my students, this is great abstract stuff, but you're not going to encounter it that much in the practical real world, except for cell phones. Vector quantization is used in pretty much every cell phone that's out there. probably an exception, but it's you know, epsilon. I just don't want to lie and tell you it's all cell phones. Now, it's vector quantization, but it's not designed using the techniques that my students and I worked on, although there are bits and pieces that are very reminiscent, and the goals are the same, except that you have to add the practice goal that you want to get manageable complexity, because usually Shannon limits, to get to them, you've got to have things that are really complex. And I chose one measure of low complexity, and practice went in a different direction. I think really for reasons that had nothing to do with which were more theoretically optimum, but simply the way that standards committees go. So in a sense, I'm sort of sad that I and several of my students missed out on this, one in particular who I'll mention. But not too sad. I guess one of the blue lines I really don't say is, what appeals to you is very important when you pick your projects, especially as a graduate student. If you fall in love with it, you're going to work 10 times as hard and find out way more stuff, and you're going to pick up the fundamentals to shift. On the other hand, there's an attitude I have found in a lot of students currently that that's ridiculous, that's not the way the world works. You have to narrow in on a particular niche which happens to have a really huge market at that time for getting hired, and focus fully on that. But, you know, face it, if you really don't like what you're doing, you're probably not going to get as far on it. And you'll get the same skills pretty much whatever you do, assuming your mentor or supervisor is reasonably general in what they do and has breadth interests. And now to the point I was about to get to, but forgot about the stuff in the middle. Theories of quantization, there are a bunch. Exact analysis, that's the oldest. How do you determine exactly what the rate distortion trade-off is? Turns out you can only do that for very simple cases like constants and sinusoids. And to a certain extent for Gaussian random processes. They just happen to be things that often work out nicely for some of the analysis. So it's really hard, but it's doable in special cases. And those special cases can be very insightful in warning you about problems. Because remember, it's a nonlinear system. And things can bite you that you wouldn't expect would happen in a linear system. So the most popular way of dealing with this is to come up with a, quote, model for a quantizer, which I will tell you about and try and warn you about. Hence the red part. What it does is basically replace the quantizer by a signal-independent white additive uniform noise. All right, that's sort of saying, I have this system and I'm going to pretend that this key part in the middle behaves like something completely different and then hope the results make sense. You know, they might by coincidence, and they might not in a disastrous way. The two theories that I've dealt most with are high rate quantization. You fix a block length and you let the rate go high and the distortion go low. A lot of people think that's actually the most important for practice. Started with Bennett, went to vectors by Zador. There's a large literature on it. The other was Shannon rate distortion theory, and I put that last because that's what I pretty much started with and knew fairly well and knew what I could use it for. And it was really these others that grabbed my interest as I got older. Okay, so here's the model. If I take the input and subtract it from the reproduction, the output, I get a quantizer error signal. All right, that says by algebra I can rewrite my system in this way. And wow, it looks like here's the signal that comes in, it's an additive noise, and out comes my reproduction. So that is often called the additive noise model. And it's no model at all, it's just a little algebra trick. And I'm serious, there's a huge literature that just starts off with this before it does any analysis. The key point is, what are you assuming about this EN? Because we've seen that there's actually a deterministic relationship of the output to the input, which is a random process. Hence, there's this deterministic relationship between the input and that noise. So when people start off by saying, okay, this is a signal-independent additive white noise, Well, it's not only not independent, it's completely dependent on the input. So that assumption is just plain wrong. And yet it's used by, I would say, 95% of the papers you see on any kind of quantization. That's usually not in the information theory transactions, but in others. So this is just, there's a red flag to be warned, to warn you about this. But as I say, by coincidence, things can still work. So it turns out that second order properties do kind of match up. And they hold exactly if you have the special case of a uniform random process that's IID, and it's uniform over the range of the quantizer, then things aren't independent, but the noise is uncorrelated with the input, which is good for spectral analysis. And the distribution of the noise is indeed uniform. And the noise is not IID, but it's white in the sense of being uncorrelated with the past and the future. So it sort of works, but you get these as good approximations. Well, they're exact if you've got the specific process I mentioned, but in general, the approximations hold only if certain conditions hold. And this was Bennett's work and a lot of people who generalized it. And they basically said that if you've got a really, really asymptotically large rate and a really tiny delta, that is, your quantization intervals are really small and there are a whole lot of them, then those results hold approximately. That is, you have uncorrelation of input and quantizer error, and you have uncorrelated or white quantizer error. So for second order analysis. Okay, those are the conditions, but where a lot of the research is, not research, a lot of the literature go wrong, especially in the sigma delta, is they use these approximation when in their case they have r equals 1. Well, asymptotic quantization results do tend to work for rates not enormously large, but kind of small, and they look pretty good. But r equals 1 is not asymptotically large. It's not even close. So those assumptions are just completely wrong in that case. Furthermore, the delta, when you look at the sigma delta quantizers, it's a 1-bit quantizer with a fixed range, and delta is half the width of the range. So again, that's just not small. So I can't teach you how this all works, but I can tell you that beware of that model. It can bite you. The most famous place that it went terribly wrong was when these things were applied to music, to audio. Well, it turned out that this model would predict you have nice smooth quantizer noise and you could make it small. But if you did an exact, well, before you did that, if you listened to it, you heard tones. Okay, if you're listening to Mozart's sonata for the clarinet or something, and you get this tone that's in the audible range, it's objectionable. Turns out the signal-to-noise ratio can be pretty good, but if you put all of that small noise into one frequency, it renders it absolutely useless. So I talked to engineers who said the theory is wrong because they were using the wrong theory. And it turns out you can analyze these kinds of feedback quantizers, but again, only for simple things like DCs and sinusoids. So that was something that I spent a lot of my career working on, and the bottom line is just beware of simplistic models. If what you get isn't what you were supposed to get, that whatever it is you're using may be based on something that's just not true. Okay, just to mention, there's a very interesting approach to patching up these problems and getting white quantizer error, which is good for doing simple linear systems analysis by adding a dither of some kind to the signal. I'll mention that again later. It's a complicated area, but in some cases it really does help. Okay, so around 1977, I think it was, started really getting into quantization, and a graduate student, when actually trying to design optimal quantizers, came up with a very simple algorithm, which is in the box, but I won't go through it. It may look familiar. I'm admitting that he rediscovered this, but it made finding optimal quantizers really easy and it worked for scalar quantizers. And then another student, Andres Buzo, found out it worked for vector quantizers. Not only vector quantizers, but vector quantizers with this really apparent, seemingly complicated distortion measure, which has a difference between the input and output, but then it's weighted in a way that's dependent on the input. So this isn't a simple difference distortion. But what's going on here is he's looking in the Fourier domain, and this is frequency weighting the various frequency, or weighting the various frequency components using knowledge of the psychophysics of the ear. So this is a very important distortion measure in speech, and this thing Linda came up with worked really nicely for it. And then it was later, before happily we wrote this stuff up, we discovered that this was all in a paper by Stu Lloyd on optimal quantization, which was originally published in '57 as a Bell technical note, but then finally published in 1982 in the IT Transaction Special Issue on Quantization. And there was also a guy who did what Lloyd did 1 year earlier, but until Alan Gershow found that reference in the early 1990s, nobody really knew about it. It was in a Polish journal written in French, but it had exactly this algorithm. Okay, this looks familiar probably because this is just the k-means algorithm, at least when you're using simple squared error. My point here is it was 10 years earlier that the quantization people figured this out than the statisticians figured out and published k-means. So I've been a bit of a, as the French would say, seme la zizanie, troublemaker, and annoying statisticians by referring to it as the Lloyd algorithm ever since, bugging my students to do the same. I guess the major point here is when you come up with a nifty algorithm, somebody very likely has done it before. Take the time to find out. Read the original papers. You'll find a lot. Okay, we used all of this stuff to come up with what was then the lowest bit rate intelligible real-time voice coder, and presented those results in 1978. And one story I'd like to mention is the very first demonstration of that. We were waiting on Signal Technology to send us the tape at an information theory workshop in Tahoe, and we got the tape and played it, and it was awful. And our great new results were just going to not impress anybody. And we were in touch with Signal Technology trying to figure out what went wrong. And then somebody had the idea of looking at the training sequence, which was the original speech, and listening to it. And it sounded awful, just like the output. So the two were very close as they should, but we didn't get a nice demonstration. That got fixed, and then we were able to play this fairly often. Signal Technology was one of the main participants in the development of linear predictive coding, and a participant in the DARPA or ARPA project to put the first real-time speech on the internet. And in order to do that, they learned that they needed, it wasn't the internet, it was the ARPANET then. In order to do that, they learned that they needed to not worry about reliability of the bits that are going across, just keep pushing them out. And that fact came into the original description of TCP, which had emphasized data over real-time stuff like voice and images. So this was a great time to be looking at digital speech. The other note, I think, was that when the paper was submitted, the reviewers thought it was too simple and they didn't like it. Thank you very much. So we just kept at it and it eventually came out. Eventually learned about the deep connections between what we were doing in clustering and learning and modeling. And two quick sidelights. The computers I was using, the famous Radio Shack PRS-80, Z80 based, you can see that instead of a disk drive, it had this cassette tape recorder. And a Chromemco System 3, which had Fortran 4 on it. This I had at home, so it was the popular house for all the kids who wanted to play games on it. So that was the most powerful computer where I lived, at at that particular time. And a lot of the Fortran development for the Lloyd algorithm went on there. Students were using, obviously, bigger tech machines and programming in C. And just the things we were using were just coming into their fame then. The story, which I'll try to make very quickly, was a student, Larry Stewart, when we were working on this, came up with what he called a hybrid code for speech, where you first quantize the LPC model, which was essentially specifying a linear filter, and then you put your possible code words into that filter to see what the outputs would look like, and then it did a minimum distortion mapping between that and the input. Okay, this technique, which he was in his dissertation and then published in '82, was at the time, we think, the best speech coding at a half and 1 bit per sample. And this is the picture which from the paper, which just showed his speech doing the LPC code word selection, that is quantizing it, and then giving a copy of the decoder implied by that for the tree search algorithm to look through it. So it was using tree codes, actually trellis codes, to get the compression. Okay, in '85, Atal and Schroeder came up with a brilliant idea of driving a code book by residuals and encoding closed loop, and using that closed loop encoding to send the right bits and information about the model. They gave it a very good name of code-excited linear prediction. There were some differences. They used a perceptual distortion measure, which had been proposed by Stewart, but Stewart's was simplistic and not the right one. And they had randomly generated codebooks instead of using Lloyd and clustering like we did. But the point is, they're given full credit, except in a few rare places, for having developed this. Stewart didn't get, in my view, anything like the credit that he should have gotten. And the moral is, first, he called those hybrid codes. That was wrong. Don't ever name anything a hybrid code. All right, nobody will know what you're talking about. Code-excited linear prediction is a really neat name, and it spread really rapidly. Larry happily enjoyed his work so much, he didn't mind that all of this stuff happened. He didn't even realize it had until I told him at least a decade later. And just how much what he had done ended up in every cell phone. The encoder was different, and the code design technique was different, but the basic idea of the closed loop encoding was exactly the same. And also, the first people who did KELP kind of cheated. They spent all their bits on the residuals, and they sent perfect LBC coefficients. For that reason, some of the original tapes and disks that showed this work were not reproducible. Because once you quantize those LBC coefficients, things change. So it was actually later than '85 that they got around to doing that part. So the regret is, I didn't go to the right places and push Larry's work. He never minded. Okay, then I got to be a full professor, and a lot of extensions on variations on what I've done before. The pictures of students are not exhaustive, and they're sort of clustered by degree time. This is Maury Ostendorf, who I'll say more in a minute. This is Larry Stewart. And I kept doing a little Shannon theory. But I realized I don't want to be reproducing Shannon theorists. And in fact, by this time, most of my reputation was in the signal processing community. And that was for a lot of reasons, but basically I got invited to do a whole lot of stuff. And I did it. I mean, I went to a lot of conferences or sent students when I can. So my information theory profile was small, but still highly enjoyable, and producing some really good students. Michelle's professor at Caltech, Phil was at Microsoft Research. Sideline, this is an example of a feedback quantizer, which has the intriguing idea that you take your input and then you quantize it, and you look at the quantizer error and then add it back to this. That is, you kind of randomize the input before you quantize it. And so this looks like a dithering system, except the dithering signal is deterministically related to the input, but through this quantizer noise, which you hope will be uncorrelated and white. You rewrite it like this, and it ends up being just the form that was made famous by Inose and Yasuda. But all of the early analyses were using the additive noise model. So they are just going to go in and replace this by a signal-independent, additive, randomly generated noise. And so, of course, their error analysis, at least early on, didn't agree with their theory. If they just physically looked at this stuff, for example, if you put in simply a constant, you have outputs that are sinusoids. If you put in a sinusoid, there you have also sinusoids coming out, and you have to deal with Bessel functions, which is really awful, but it points out what's going on and what's wrong with the analysis. Side interest in here was I found out about almost periodic sequences. You learn about periodic sequences in your Fourier analysis and systems courses. And it turns out if you get slightly away from that, things still work. And there's this great little book I discovered, one of the classics I mentioned, by Harold Bohr. He's the brother of Niels Bohr. He was a mathematician. This is another one of those theories that just might crop up someday. That was another paper. It was thrown out by the editor without review as being too mathematical. I pointed out that many of the papers published on sigma delta had pages and pages of math that theirs was incorrect. They were trying to simply patch up the additive noise level by all sorts of tortuous approximations. But their papers were longer, but he projected it. So the good news was we went on to publish this stuff in several places, and I think had a real impact. The even better news was the fact I had a built-in excuse to refuse to review any papers for the transactions on computer systems, on circuits and systems, for the rest of my career. And I always got to tell them why. So I had a bit of revenge. I'm not saying you should, go for revenge, but I also got into the theory of dithered quantization and ended up writing a paper with Tom Stockham, who's generally credited as being the father of digital audio. And that was a lot of fun and straightened out a lot of misconceptions and errors in the literature, some of which are out there still. If you go to the giant and Knoll book on digital communications, everything they say about non-subtractive dither is wrong. It's there. When I wrote him to point out these errors, I got a nice letter back saying, thank you very much for your comments regarding our book. I will try and look at them when I get the chance. Don't write letters like that. Because it's very clear the person is never going to look at it, and they're past that. Got looking at trees with Tom Lookabout, as well as Phil Chow and Eve Riskin. Then got into medical imaging, and there you see Pam Cosman. Spent several years at that. I have to admit it was highly difficult because we were dealing with medical communities and statistical communities. We had good help in the statistical area from Richard Olshan, who ended up being the second reader for a whole bunch of my students. Worked in a variety of areas, but the key idea was how do you show that if you're using compressed or even digital medical images, there is no effect on the diagnoses based on those images, or if it's a screening study, they are not affected. Or if they are, that they're affected in a beneficial way. And that got us into a lot of arguments and fights with the established medical statistical community. But I think we had an impact. We testified before the FDA. Our main point was a lot of the alleged research being done basically had a whole lot of images and then hand them to a radiologist, maybe two, and asked if they thought the images were nice or not. We had a collection of MDs who in very careful ways were doing screening work, some cases diagnostic in small studies, and we would compare randomized things at various bit rates And we looked at distortion in the design, but we didn't care about signal-to-noise ratio in the application. Our concern was, are these images reliable, valid in those applications? And bottom line was this quote from one of the presentations we made, which basically said you could go from high-rate digital stuff at 12 bits per sample, which was what they were using at the time, down to about 1.5 sample with no statistically significant differences in the, let me get the wording right, in the patient management, what the doctor actually did. So one point was that a substantial part of the medical community was frightened of anything digital at all because of lawsuits. If the image isn't perfect, the doctor could make an error, and this justified the use of them. The second was when they were doing lesion detection and actually trying to mark a lesion, there were some differences, but they were equally balanced between the quantized doing better and the quantized doing worse. So at least all of this stuff was a candidate. This resulted, by the way, in some of those PhD students never touching anything medical again, because this was so hard, and with at least one dropping out of the PhD program to go to medical school, because she got so enamored of that side of the thing. Okay, this is when the culture changed in my group. Mari, whom I pointed out before, joined about 1982. She got her degree in 85. In those days, there were very few women in EE. I think there were maybe 2 in our part of the EE, in ISL. And she succeeded. I have to admit, I noted a lot of differences in the ways that she approached things and thought about things, and I learned differences in the group dynamics, which did change when she joined the group and people adapted. But her success did a really nifty thing. I mean, I can't claim to be an altruist. I was selfish. All of a sudden, I had all of these great women students. I mean, all of a sudden, these are small numbers we're talking about. Happened over a few years, but many of them had funding, and many of the others I found funding for. And so by about a decade later, my group was only almost half female. And just for amusement, this guy in the upper left wasn't even a member of my group. He just thought the group was so cool, he wanted to be in the photo. He did come to meetings, though. And this is Richard Olchen, my colleague I pointed out before. Okay, my students put me up for an award which I won, which was the Paceman that Todd mentioned. And there was a charge in that to use 10K that we got from the NSF, 10K from Stanford, to put on a workshop on mentoring. And like a technical workshop I'd done as an assistant professor, we organized that every session had somebody taking notes. Every speaker gave a copy of their slides and in some cases wrote it up. And we produced this little book, distilling the wisdom of people who were both beginners at being faculty, who were senior faculty, and who were graduate students. We had a lot of fun. This is still available. If you're interested, I can tell you the PDF, or you can get hard copies from my assistant at Stanford. As a result of this, I got invited to do a follow-up workshop at the Banff International Research Station. If you ever have an opportunity to go to or organize a workshop for that, do it. It's unbelievably gorgeous, and they have wide, free times when you can go hiking and discuss whatever the research is. That was a picture taken there. And so that had a smaller group, but still both of those things I really enjoyed, and I should point out that the workshops really were among the most fun things I ever did, and the production of the books. I also got invited to do another historical thing which got me connected with the history of digital speech and with the internet. I'll just point out, I was with these very famous people like Larry Rabiner and Jim Flanagan and Itakura and McCool and Ron Schaefer, who were in on the ground floor. I wasn't. My brother was, and he wouldn't go to Hawaii, expenses paid. So I got invited to talk about the California part of the development of those projects, and had a ball. wife loved Maui. I did too. I also became vice chair, which I did for about 14 years, which got me into some administrative work, much of which I enjoyed. Actually had an impact, I think. And it got me out both of the research offset requirements and lowered the teaching level. I really could pick what I wanted to teach and when. I was in charge of the teaching program, so I sometimes either had to cancel the class or teach it myself. And I did the latter a few times, but that was fun. And working on quantization stuff with Tomasz Linder and Jali, who's at Penn State now, got very interested in the simulation problem, which I wrote, but that's basically, in a nutshell, you have a given random process. I would like to find a constrained random process that is something that's stationary and ergodic and has a particular form. The form is you get it by taking an IID process and putting it through a sliding block code. Those are called B processes by Ornstein. And they have a lot of magical properties in ergodic theory. So the question is, what is the best fit in the terms of that D bar distance of all codes in that class that have radar? And perhaps anybody who's had information theory will know it ends up not coincidentally being the Shannon distortion rate function evaluated at R. And that actually suggested a bunch of techniques for coding. Okay, final thoughts. These are the things I couldn't fit in before. So almost done. First, health. The biggest unpleasant surprise about the time of retirement is I think our bodies come with warranties. And they expire when you get into your late 60s. And before you're ready, things start going wrong. I basically retired because of health problems. I had to start spending at least half my time dealing with those health problems. So just realize that's going to happen. Plan accordingly. Don't postpone everything that's fun until you retire. You could end up having not being able to do it. So it happens. Do everything you can to stay in good shape. Just pay off well as you get older. History. I've had a good run writing historical articles in one book. And there have been a couple of times in my career where I was simply associated with people who really got famous for inventing things, like the internet, like digital speech. And they didn't write the books themselves, and it helped me write a history of the first real-time digital speech on the internet. I should add, you probably know this, this crops up somewhere, you probably know this as voice over IP, but voice over IP happened before IP, and is one of the reasons IP is the way it is. Because IP in one of the original implementations would not have worked with real-time signals. It would have worked fine with computer data, but not with voice and images and movies and videos and everything like that that you think about. So even though my memory is bad, I knew a lot of these people involved, so I spent a couple of years going around and doing oral histories, collecting it, writing it up. And when you discover something brand new and neat, check very carefully to make sure it doesn't exist somewhere else. Like there are, in the Earth movers distance, there are hundreds and hundreds of papers that have been written in those. And Todd mentioned Villani. He's written a couple of books on optimal transport, which I strongly recommend. He's a very interesting guy. Learning both about what he's done and himself personally, I think is worth the effort. Also, if you go into academia, or even if you go into industry, the junior people you work with may often lead you into new areas you would have never considered without them. And in fact, when I did my PhD thesis, Bob Schultz knew nothing about rate-distortion theory. He was willing to learn it as I did, read the same things that I was reading and go through it from the start. So my mentor sort of taught me that part of mentoring was, it's not a one-way channel. You can learn a lot from your students. Also, job markets change. I had a whole bunch of students do it when it was popular, and then the bottom dropped out when they graduated. So almost all of them went into networks and other places. They had the random processes, probability, all of the tools that they needed, so they just shifted. I think only one of them ever returned to speech. Diversity of all kinds is a good thing. I didn't discover that really until about 1982. But after that time, if you read either of those books, I did everything I could to recruit a diverse group of students, and I think was successful at that, and really had a good time with that. I just mentioned this example. Beware of the new that is actually old, and similarly, beware of technical fads. I give you examples here of things that got rediscovered. I don't really hear because some of the technical fads are extant, and I may be wrong. So I'm not going to embarrass myself or run that risk. Sometimes they work out. The first papers written on compression using wavelets were absolutely nonsense and showed that the people dealing with it had no clue what compression was about. But eventually, the compression people got involved enough, and they figured out the algorithms to make good use of wavelets, and all of a sudden, there was a whole new world for data compression. Read the classics. I just listed a few, and I mentioned a couple of others in the talk. This one I have to add. If you get a chance to work with somebody really smart, take it. Even if you end up having to do most of the work. It's just, as I said, that paper with Ornstein and DeBruschen is something I will never forget doing, even if it was arduous. And just lastly, consulting was something I tried seriously at the start, but then instead got more into parenting with that time, writing books at home because I couldn't combine those two things. And years later, discovered that because of my historical interests and because the patents were starting to get applied for, I had no trouble getting consultant doing intellectual property kind of stuff, especially for stuff related to speech and image coding, because those were about not what was the most modern, but really who did what first. And so handling attempts to patent things like transform coding and being able to shoot them down. So that paid for several deck replacements in the wooded town we lived in. Okay, with that, I will thank you for your attention. I hope I've passed on some things I've learned over the years, and except for lunchtime, I'll be around today and tomorrow morning if anybody would like to chat about it. I don't know if there's any time for questions left. So when you're talking about historical stuff, it's easy to wander.
Well, let's first give Bob a big round of applause.
We're very fortunate to have Bob here, so I say let's definitely invite some questions, technical or otherwise.
One of your last slides said diversity is good, but beware of the interdisciplinary.
Ah, yes, I missed that. That's largely because of my experience doing the medical research and because of my experience being a vice chair. It can be fun, but it can be very dangerous because people who are doing interdisciplinary, if they become a professor, eventually come up for tenure. And the way tenure committees mostly still work is you will look for the one field where the person has made the most impact and go out and quiz people only in that field. When in fact what the person may have done is done a combination of stuff spanning fields, each of which is an impulse, but maybe not with the area to succeed in one area. So one place is simply the career in universities. Universities encourage interdisciplinary, but I think they're still struggling with how you promote somebody who has a home department and they go to a limited number, not somebody as broad. There may not be anybody as broad to really appreciate. And just the mechanics of getting the funding and managing and working with MDs, MDs whose training does not include the scientific method and go about things in very, very different ways when putting together experiments. This can work out. I think the experience was good. This, in general, this is something you can also ask Pam about, but it was really painful at times. We were in some pretty heated arguments with alleged experts, talking about their analysis of validity of a method by using ROC curves. How many people still have encountered these? Are they even around anymore? Something operating curves. It used to be a standard way of analyzing detection error trade-offs in additive white Gaussian noise systems. And it was everywhere. And the trouble was they were applying it to things where you didn't have white additive Gaussian noise. And they were making all of these stretches of conclusions based on it. And none of them were actually testing what it was all about. That is, what is your diagnostic accuracy? Or what the physician actually does, having seen the result. Not SNR. Because physicians justifiably don't care about SNR. So that was the warning. That you're asking for trouble if you do it. Just be aware of it, because people survive it.